Welcome. This is the first lecture on solutions. This first is a little bit heavy on vocab, so make sure you follow along with your skeleton notes and get those vocab words done. And then we'll be talking about molarity and dilutions in this. So here we go. So solutions are a homogeneous mixture of two or more substances. What that really means, homogeneous means it looks the same throughout. An example might be our disinfectant spray. It looks yellow all the way through. You don't see any different layers or anything, but there's more than just water in here. There's water and some chemicals, obviously, we know. So this is a good example of a homogeneous mixture. Another example might be Mr. Foss's Mountain Dew. It's got more than water in there. It's got carbon dioxide. It's got some sugars and stuff in there. So those are all good examples of solutions. Now, we have some properties. These are very, very small. Evenly distributed. That's why it looks all the same all the way throughout. And no matter how long I let this bottle sit in my room, those particles that are in there are not going to separate out. We're not going to see two layers ever. So that's the three properties of our solutions. Again, you've watched these videos before. I may go a little fast. Stop if you need to copy down and pause. Try to keep the videos down to a short time. Our first term we need to know is the solute. The solute is the stuff that is dissolved in the substance, and a good example of this is salt. Now, you need a solvent to do the dissolving. And now there are other solvents than water, but in our class, water will be pretty much the only one we use. One way to remember these is the solute is the smaller one, the solvent is the bigger one. And if you look at it, the word is a little bit shorter, solute, so that reminds me that that goes on top, or that's the one that's being dissolved. Now, we have soluble, very close to both of those words, but soluble means it will dissolve in water. Now, I remember that sodium chloride will dissolve in water or table salt because I used to play a little joke on my dad, and we'd go to a restaurant and get some water, and then I would dump a bunch of salt in his water when he went to the bathroom, and it would dissolve in there, and he couldn't see if it was in the water, and then he would drink it, and oh boy, did Mr. Foss get a scolding for that one. And then there are other things that are insoluble. They just don't dissolve into each other. And that would be oil and water. And I have an example here. I have a clear liquid and a green liquid, and they just won't mix. I can even shake this up, and it looks like it mixes, and you can see right away they start to settle out. So this is insoluble. All right, we really have more than just liquid solutions. We have solid solutions, and these are your alloys you hear of, metals mixed together. And we do that to make them, most of them more stronger, some we want more flexible. In our class, we won't deal a whole lot with them, but there are solid solutions. Now, there are gaseous solutions, and that makes sense because the air we breathe is not just all oxygen. There's nitrogen, actually mostly nitrogen in there, and some argon and some other things in there, obviously. This gaseous solutions depends on the components in there. Now, I will say that like some gases are very explosive or reactive, and some are very inert or don't react. So Those properties depend on the actual things that are in that solution. Now, liquid solutions are what we're going to deal with, such as Coke or Mr. Foss's Diet Mountain Dew. We can talk about them being miscible, which means they can form a solution in any amount. Doesn't matter how much you have, they'll mix together really nice. Or immiscible, and that can not form a solution. And again, the great example of that is oil and water. Now, quick quiz for you. The clear and the green. One of these is water, one of them is oil. Which one? Think of an oil spill out in the ocean. What happens? Yep, oil rises. So this is our oil and this is our water. Oil is less dense. That helps this being immiscible. In aqueous solutions, these are normally all we work with. We use water to dissolve stuff. Now you can see here that we talk about water being the universal solvent. People would say that water can dissolve anything in a long enough period of time. Some of those periods of time are longer than we are alive, but water dissolves most everything. We'll get more into that as we go, but water is normally our solvent we use. Now, in these aqueous solutions, we can ask ourselves, is it an electrolyte or not? And an electrolyte is an ionic compound. And just to remind us what ionic compounds are, I'm going to do CaCl2. That's an ionic compound because it will break down into Ca2 plus and 2 Cl minuses. Those charges up top remind us that it's ionic. That will make electricity. Lightning storms, you're not supposed to be in a pool. Well, there's ions in there, and obviously those will conduct electricity. And then if we have electrolytes, we have solutions that aren't electrolytes, and that would be non-electrolytes. And that's like sugar. Sugar is a covalently bonded molecule, so it does not have any of those. Most of us have heard electrolytes in our sports drinks and stuff like that. And that's to bring back those ions that we lose from sweating. All right, to our major math concept, concentration. Now we talk about concentration all the time. Maybe you make Kool-Aid at home and you like more sugar. That would be a more concentrated Kool-Aid than maybe Mr. Foss would like. So we use the word concentration in our everyday language, but in science, we use molarity. Now, molarity is the moles of the solute over liters of solvent. Now, again, we go back to our definitions. Solute is the stuff that's being dissolved, and the solvent is the stuff that is dissolving the stuff. And then most of the time, we are going to talk about water as our solvent, and our solute can be anything that we talk about. In this concept, as a whole in chemistry is pretty important. All the solutions that you use and make or will make now are based on this concept. I would really push that this big M, and we got to use big M, capital M for it, you break it down into the moles per liter. And I'll show you. Let's do a couple practice problems. So here, the question says, a solution has a volume of 2.0 liters and contains 36.0 grams of glucose. If the molar mass of glucose is 180 grams per mole, what is the molarity of the solution? Well, again, I'm going to write this up here, big M, and we can't use small m, and you'll see that in a later lecture, but this is moles over liters. Now in this problem to start with, we're pretty lucky. It gives us our liters. So we already got the bottom number. Now we are starting with 36 grams of glucose, but we want moles. So here's a one-step dimensional analysis, 36.0 grams, and there's 180 grams in 1 mole. And when we quickly do our math here, 36 divided by 180, I get 0.2 moles. So now we have our two things we need. We need moles and liters. So let's just put those together. 0.2 moles divided by 2 liters. And we get, make sure Mr. Foss does his math correctly, we get 0.1. And let's label this correctly. You could do moles over liters, or now that we know this term, we're going to use big M, and then we would write glucose on the end of it for a perfect label. So that's the concentration of glucose. We do these concentrations a lot. Nurses that put saline solutions in people and stuff like that need to know these concentrations. I would argue the biggest thing about this is knowing your units. What do you have? What do you need to get to? I can ask all sorts of questions. I can give you the molarity, ask for how many liters you need. I can give you the molarity and ask you how many moles you need. Anything of those I can do. Let's try one that's really straightforward, to be honest. Here we go. A solution has a volume of 250 milliliters and contains 0.70 moles of sodium chloride. What's its molarity? Again, we know our basic idea here is moles over liters. At first look, we may think we've got everything because we do have moles, that goes right down there, but we got to check our units here. That's in milliliters, so we have to change that. You don't have to show me that work anymore. I trust that we can make that quick conversion. This is the only amount of work that I would need to see. And in this answer, 0.70 divided by 0.250 equals 2.8 big M, or you could write moles per liter, but big M is easier, of sodium chloride. Now, you'll see in your homework that it starts off mostly pretty simple like that. I change it up a little bit down by number 5 and 6, but the concept of molarity is just moles per liter. Make sure you're looking at your units when you do this. Now, what goes hand in hand with molarity is dilutions. Now, what we're doing here is we're starting with a really concentrated substance, and we don't want it that concentration, so we dilute it down. You make your Kool-Aid, dump all that sugar in there, and you're like, whoa, too much? Well, how do you change that? You add more water, and that's the exact idea here. But there's a cool equation that makes life pretty simple for us, and it is called M1V1 equals M2V2. Now, M stands for molarity, and V stands for volume. So truthfully, the volume should always be in liters, but if you use volume the same all the time, like if you use milliliters and milliliters, it works its way out. So you don't have to convert. That's just the beauty of this equation. Let's try 2 practice problems. So this says, how many milliliters of a solution of 4.00 big M molarity of potassium iodine are needed to prepare 250 milliliters of 0.76 molarity Ki. So let's start with our equation. M1 V1 equals M2 V2. Now you could set this up any way, but I really like to put the M1 as my stronger concentration. So here is our 4.0. That's the molarity. It wants to know the milliliters of that solution. So we are really looking for V1. That's our X, because we want 0.760. And how much molarity of that do we want? We could change it to liters, but I'm going to make things easy. Keep it in milliliters, because the answer wants to be in milliliters. Now, to do this, I'm going to do every step on this one. I'm going to multiply 0.760 times 250, and that gives me 190. And over on the left side, we still have our 4.0 and X. Now, to get X by itself, we're going to divide by 4.0 each side. And that gives us X, or how many milliliters? That gives us 47.5 milliliters. Now, let's take a second to think about this. We're taking a concentrated stuff and we're making less concentrated. Now, we are needing 47.5, but I'm trying to prepare 250. So what's the other stuff? What's the leftover that I need? Well, that's just water. So if I need 250 and it tells me I have to use 47.5, well, what's the rest of that? Well, the rest of that would be water. And in this case, we would fill water up to 202.5 milliliters. Let's try one more. All right. The question asks, how could you prepare? So we got to kind of talk this one through. It's not really a number. We got to use some words here. So how could you prepare 250 milliliters of a 0.20 molar sodium chloride solution using a solution of 1 molar in water? Well, we kind of talked about this through that first one, but let's do it one more time. Now, again, Mr. Foss will always put the higher concentration on the M1. So that's a 1.0. We want to know how to prepare it. So it's kind of like the same question. I want to know how much of this stronger concentration I need to use. So our math is the same as what we did before. And I'm keeping it in milliliters because we don't need to change it. But just remember, our V1 is going to be in milliliters. So when I do some quick math here, 0.20 times 250, 0.20 times 250, I get 50, and this is 1.0 and V1. Now dividing that over, I can do that in my head. V1 equals 50 milliliters. So we got a little bit of words that need to be involved here, so I'm going to talk it out, just like I did the other one. We want a total of 250 milliliters of this 0.20 molar solution. Well, from our math, we know that we need 50 mils of the 1.0 molar solution. So what is the rest, or the 200? We would say we need to add 200 milliliters of H2O. And that's how we would prepare that solution. All right. So if you get a chance, work on, it says up top, it says molarity practice. Sorry about the first question. There's a big space in there. I'm not sure why. And then dilution practice, you can start on those. And then when we get to class, we'll go over any answers and questions. A couple of them might put a wrinkle in it, but most of these are pretty straightforward. Again, thinking of your units when you do most of these. All right, we'll see you at class.